Welcome back, students. Today, we are going to take our first look into electronic spectroscopy, specifically of molecules. We've already done this with atoms, but as we've seen, molecular orbitals are different than atomic orbitals, and so we have different ways to talk about their electronic spectroscopy, and of course, different selection rules, and so forth. So we'll start today with a simple introduction to electronic spectroscopy that will focus on things like the nomenclature of the molecular orbitals in the excited states and talk about the selection rules and which transitions are possible. The goals for today are going to be able to determine the term symbol for the ground state homonuclear diatomic molecules. This will be very similar to the way we developed term symbols before for atoms. And then we're going to want to be able to state these selection rules for electronic spectroscopy. So now that we understand the differences between atomic orbitals and molecular orbitals using molecular orbital theory, we can begin to investigate the transitions that molecules make as you excite them, as they absorb light. As you're aware by now, electronic spectroscopy takes a larger energy light because the separation between electronic energy levels is much greater than any other degree of freedom that we've talked about before. So electronic transitions are higher in energy than vibration and rotation. They take smaller wavelengths of light, higher energy light to excite those. And these are typically in the ultraviolet range, and some molecules do have electronic absorption in the visible range. And when molecules have these absorptions in the visible range, that is actually what's responsible for their color. And we've talked about that before with Huckel theory last time, and we saw that in our second lab where we did UV-vis spectroscopy of these conjugated polyenes. We saw that the octatetraene actually had a yellow color because it absorbed purple light. And this is true broadly for all organic molecules. And so now it's fall, we can see all the pretty colors in the trees. And the reason we see the pretty colors in these trees is because the chlorophyll, which is a highly conjugated molecule, is being degraded in the leaves. The trees are no longer maintaining the chlorophyll. And so the chlorophyll that strongly absorbs purple and red wavelengths of light, thereby emitting green wavelengths of light, is now breaking apart. And so what we're left with is a whole bunch of other molecules, such as beta carotene and others, that strongly absorb only blues and purples. And so what colors they reflect tend to be more orange or red. And here in Michigan, we actually get a whole lot of nice colors. We see like pinks and yellows and really bright oranges and so forth. And this is because of these molecules are highly conjugated, allowing them to actually absorb some wavelengths of visible light. Another example that we can see are things like flowers. So some flowers are colored, some flowers are white, and even flowers that are white actually can have patterns. So this flower appears yellow to us, but it actually has differences in the pigments of that flower that are absorbing specifically visible wavelengths of light, which some birds and bees are capable of seeing, which make them more attractive to pollinate and so forth. So electronic degrees of freedom absorb these high energy lights, and we, just like other types of excitations here, we transition from lower energy to higher energy. And we'll look into this more in the next lecture, but just like when we absorb infrared light, our vibrational transitions were accompanied with rotational transitions. When we excite molecules electronically with such large energies of light, we also excite vibrational and rotational transitions. And we'll go into more detail about this in the next lecture. Another important thing to keep in mind is that absorbing these high energy ultraviolet photons actually is much more disturbing to molecules. It does a whole lot to things like the bond length. And you've probably remember from organic chemistry that you can even use certain wavelengths of light to excite dissociation reactions and make radicals. And that's because these wavelengths of light have a whole lot of energy, and in some cases are even capable of breaking bonds. The first thing we want to look into when thinking about electronic transitions is how do we talk about the levels that molecules have? And it turns out that the way we do this is directly analogous to atomic term symbols. So just like our atoms had term symbols like 3p, 1d, 4f, whatever our term symbols are, we have the same thing for molecules. To specify that we're talking about molecules, instead of using the Latin letters, SPDF, we use Greek letters. So our S terms become sigma terms for molecules, and our P become pi terms, our D become delta, and then F becomes a phi here. Now, unlike atomic terms, it turns out that our molecular energy terms are actually generally quite simpler than the atomic terms. Now, why is that? What made these terms complicated for molecules? Well, they had things like high orbital angular momentum, and they had high spin, and so forth. You could have, right, we could have up to 5 electrons in a d orbital unpaired. Now, for molecular orbitals, at least in this class, we're not going to be considering d orbitals. I'm sure making d molecular orbitals complicates things. But for just thinking about molecules with normal sigma and pi bonds from s and p orbitals, the most degeneracy we ever saw was 2. The pi bonds are 2-fold degenerate. So we don't even have something like the complexity from 3-fold degeneracy like we saw when considering the p orbitals. And that actually makes the terms a lot fewer and more easy to account for. So we'll go through a more complicated example of this with diatomic oxygen in the next slide. So we can also apply our G and U symmetry, but we'll typically only apply this to homonuclear diatomic molecules. And that's for the same reason that we only applied it to homonuclear diatomic molecular orbitals, in that when you have a heteronuclear diatomic molecule, we don't actually have that kind of symmetry that's built into that G and U designation. We don't simply change sign upon rotating around the axis there. So we can think about this by starting with a simple example of determining the term symbols for ground state and excited state H2. Now, this is directly analogous to the helium atom that we've done before. In the ground state, we're going to have 2 electrons paired in this lowest energy molecular orbital. So we would think that that would give us that L is the same, so L is only equal to 0, and then since the spins are paired, S is equal to 0. So for the helium atom, the ground state helium atom, and the ground state every atom when every orbital was full, it was a 1s state. And so that is going to be the same for diatomic hydrogen. We're going to have 1s, but since we're talking about a molecular orbital, we use sigma. So we'll have a 1 sigma state for the ground state of hydrogen. Now, for the excited state, what can we say? Well, in the excited state of diatomic hydrogen, we'll have 1 electron in the ground state, 1 electron in the excited state. And in this case, they're both sigma orbitals, so the L is both 0 for both of these. But what we can have is we can have paired or unpaired spins. And so the paired spins, like before, will give rise to a singlet state. The unpaired gives rise to a triplet state. And just like excited helium atoms, where we have a 1s or 3s term, we could have here a 1 sigma or a 3 sigma term. And we can see the results here of these states. Now, to properly designate these, we can do things like add G's and U's. This is a little bit more complicated than we're going to want to get into, so don't worry too much about applying G and U symmetry to these terms. But the one thing we do want to be able to apply is plus and minus superscripts, especially for the homonuclear diatomic molecules. And so we can apply these superscripts based on these following rules of thumb. And again, these rules of thumb work for homonuclear diatomic molecules. So if all of the MOs are filled, we have a plus. So for our ground state, we would have 1 sigma G, then we would put a superscript plus here to denote that symmetry. If all partially filled MOs are sigma, which is the case for both of these states here, we would also add a plus. Now in the case that the partially filled MOs are pi's, and we'll see this for oxygen, the triplet state gets a minus and the singlet state adds a plus. If you're interested, there's a supplemental section in the back of this chapter, chapter 25, that goes through this. We're not going to cover this in class, and I'm not going to expect you to know it, but you can check that out if you are interested. Now, what do we do for a more complicated atom like oxygen? Let's go ahead and look into oxygen. The first thing you're going to want to do is construct and fill an MO diagram. And then we're going to look in and try to figure out what we can say about ML and MS and S in the same way we did for oxygen, the oxygen atom, and carbon atoms before. So I'm going to bring up the board here and we're going to look into this. So here I have the molecular orbital diagram for diatomic oxygen. And what we want to do from here is consider what the orbitals are and what we can say about their terms. So remember, and this is the same for atomic spectroscopy, is what kind of orbitals did we consider? Well, for atomic spectroscopy, we only considered the unfilled orbitals. So for molecular oxygen, we had something like 1s2, 2s2, and 2p4 for the electron configuration for oxygen. And all we needed to do to determine the terms was to look at these unfilled electrons here. That's the same thing for these more complicated orbitals. So all we need to do is consider these unfilled electrons here in the 1 pi g antibonding orbital. So here we can see we have 2 orbitals and 2 electrons. So we actually have a whole lot less options than we did before for atomic oxygen. It actually gets simpler. So we'll go ahead and explore this for molecular oxygen. And we have 6 different combinations that we could have. So we'll go ahead and draw out 6 combinations here, and we'll fill them in with electrons. So the first thing we could have is both electrons paired in the same orbital. We could also have them in opposite orbitals with spin up and both spin up. We could have them in opposite orbitals with spin up and spin down. We could swish the spin up and spin down. We could have them in the opposite orbitals both having spin down, and we could pair them in the second orbital here. Now, before, when we were doing this with p orbitals, we said, well, we have an ML of 1, 0, and -1. We went through and we calculated this. But what do we do here? How do we know the M sub L? These are pi orbitals, and what are the pi orbitals coming from? So the pz orbital makes a sigma bond, and so the pi bonds come from the px and the py orbitals. You might not remember this, but if we go back to look at our hydrogen atom orbitals, the pz orbital has an ml equal to 0. When we have ml equal to 0, we only have theta dependence, which gives us our orbitals pointing in the z dimension. So therefore, the x and y orbitals are coming from having an ml equals 1 and -1. And just like before, when we were doing atomic orbitals, we can label these with both just 1 and -1 arbitrarily because we're talking about all the combinations. From here, we simply determine M sub L and M sub S and assume that those are the maximum L and S like we've done before. So we'll have M sub L, M sub S. In this case, we have an M sub L is equal to 2 and an M sub S is equal to 0. In the second case down here, we have an M sub L is equal to 0 and M sub S is 1. Then we have 0, 0, 0, 0, 0, -1. And finally here we have a -2 and the 0. So what can we say about these states? Well, first we'll note that we don't have any M sub L is equal to 1. So in this case, we don't have all of the possible combinations like we expect and like we see in atomic orbitals. We only see a subset of these. But we can do a similar sort of thing and pair off these two with an M sub L equal 2 as being in the same term. So the M sub L of 2 and the M sub L of -2 are corresponding to a 1 delta term. The delta coming from having an L equal to 2 and the 1 coming from having an S equal to 0, because that's still 2S plus 1 up there. Now, when we have an m sub s is equal to 1, we can see we have a state with an m sub s is equal to 1, an n sub s equal to 0, and m sub s equal to -1. So we can put all three of these guys together into a state with m sub l is equal to 0, so a sigma state, but an m sub s equal to 1, which would be a triplet state. The last guy here has his own state that will be a singlet sigma state. And so these are the three possible terms here that we can have for molecular hydrogen in the ground state. And how do we rank these? We simply rank them in the same way that we would for atomic orbitals using Hund's rules. So Hund's rules say that the largest spin multiplicity is lowest in energy. So that would be the 3 sigma term. The next term, lowest in energy, they're both singlet states. One of them has a higher orbital angular momentum. So we have the singlet delta state next, followed by the singlet sigma state, highest in energy. Using our rules from before, we can determine the G's and the plus or minus of these. In this case, our unpaired orbitals are in a pi G orbital. So all of these end up getting G's. And for the plus and minus, the delta state does not get a plus or minus. The sigma states get plus or minus depending on what we have. And our third rule that we talked about before, where if we had partially filled pi MOs, the triplet state gets a minus and the singlet state gets a plus. So these are the complete terms for ground state molecular oxygen, where the 3 sigma G term is lowest in energy. Going back to the slides here, we can see the ground state terms for all of the second row diatomic molecules. One thing to point out that I mentioned before is exactly like we expect from atomic spectroscopy. If all of the orbitals are completely full, our ground state is a 1 sigma G. So we see for diatomic hydrogen, we have 1 sigma G. For diatomic lithium, we have 1 sigma G. We also have that for carbon, nitrogen, fluorine. Only states where we don't have completely full orbitals have ground states that are not 1 sigma G terms. Another thing to point out is that since, again, we're dealing with these simpler systems, we only see singlet states or triplet states for molecules. It's pretty hard to see non-singlet or triplet states. And that's where the emphasis from singlet and triplet comes in. These states here that have doublets, these are all ions, right? So we have H2, He2 plus, and then N2 plus, O2 plus. So if we have ions, we can get these doublet states. But if we have normal molecules, we always have either singlet states or triplet states, even if we're excited. And that's where we have this emphasis on singlet and triplet states. Whereas that wasn't as clear with atomic spectroscopy, where we saw all sorts of doublets and quartets and various kinds of states, depending on the atom we looked at. The next question we want to ask is, what are these actually going to look like, and what happens when we excite electronic transitions? When we do this, we actually go through, like I mentioned earlier, a big change in the molecules. We don't simply move from one state to another, like vibration. Our vibrational angle doesn't get a little bit larger, but we actually go through some pretty radical transformations. So if we think back to the MO diagram we just drew for oxygen, if we were to excite that oxygen molecule, we would likely get more electrons in antibonding orbitals, which means our new molecule has more antibonding character, which means that it is less stable. It's going to have a longer bond length and so forth. So it is best to think of these molecules as having this energy well. And we've constructed these energy wells before in lab. And think about transitions from electronic states as going from one energy well to another. So here we can see our ground state atom here. And the ground state, so we have our 3 sigma G for oxygen. We label the ground state for molecules with an X. And you might remember this when we were looking for the constants for hydrogen chloride. We had to go through and scroll all the way down to the bottom of the NIST webpage, and we found some thing that said X something something something, and it was Greek because it was talking about the term of the HCl molecular orbital in the ground state. And this is the lowest energy term here. We give it an X. Higher energy levels are labeled with A, B's, and C's in just going down the alphabet. We get lowercase letters if the spin is different than the ground state, and uppercase letters if the spin is the same as the ground state. So if we look here, this yellow curve is our lowest energy ground state here. The green and blue curves are the delta G, the one delta state and the one sigma state. And since they're singlets and the ground state is a triplet, they get lowercase letters. So this is lowercase a and lowercase b. We have other states that account for excited states that have an uppercase a and an uppercase b because these happen to both be triplet states. And we could come up with many more states for oxygen if we wanted to. Now, just like any other type of spectroscopy, there are selection rules for molecular spectroscopy. And we'll go over and talk about the selection rules for molecules with the atomic numbers less than 40. And we have spin orbit coupling when you get to larger atoms and molecules, so we're going to ignore those for now and just focus on these simpler models. So in this case, our main selection rule that we're going to follow is that delta S equals 0. So the transition from a singlet state to a triplet state and a triplet state to a singlet state is forbidden. And that's part of the reason why we have different cases here. We have lowercase and uppercase. So going from X to the lowercase levels is forbidden. We're going to look into this more in a couple of lectures and kind of see the nuances here, because what's going to happen is molecules are going to find their way into triplet states through non-radiative pathways, and then it's going to be very hard for them to get back to the ground state since that transition is forbidden. And we'll talk about that. That's a process known as phosphorescence. And we'll talk about that in a couple of lectures. Another selection rule is that the delta lambda has to be 0 or plus or minus 1. This is very similar to our atomic spectroscopy. We also have other selection rules that if we're in a U state, we have to go to a G state, or if we're in a G state, we have to go to a U state. So U to U and G to G transitions are forbidden. And we also have to obey a plus state must go to a plus state, and a minus state must go to a minus state. We can't convert from plus to minus. Again, the reasons behind this are complicated, and we're just going to focus on the actual rules here. So looking at our oxygen here, what transitions can we actually see? Well, we can't go from our triplet ground state into either of these two singlet states. So those are both forbidden by the delta S equals 0 selection rule. The going from the X state to the A state is also forbidden because it involves a minus to a plus transition. So therefore, the lowest state transition that we could observe here for diatomic oxygen is going to be to go from the ground X state to the excited B state here. And to accomplish that, oxygen has to absorb ultraviolet light. And this makes the oxygen in our atmosphere a filter for harmful ultraviolet light that then can't get through the atmosphere as well to get to us, where it's damaging to us, gives us sunburns, damages plants, and so forth. It's also involved, absorbing ultraviolet light is also involved in dissociating oxygen and turning oxygen into O3, into ozone. Ozone is an even more potent absorber of ultraviolet light, and its presence in the atmosphere is formed by oxygen molecules absorbing ultraviolet light, and it's very important, again, for keeping ultraviolet light rays outside of where we live. And so we'll stop here now that we've thought a little bit about how electronic transitions happen. And what we'll look at next time is what is actually happening to molecules as they absorb light. So if we were to start in this X3 state, in the ground state, where we typically are for these molecules, and excite up into this B state, what is actually happening to the molecules? What vibrational and rotational transitions are accompanied with it, and how can we describe this? So we'll look at that next time, and then following that, we'll look at some applications of electronic spectroscopy and what we can do with it. So I'll leave it here for today, and I look forward to talking about this with you guys in class.